My name's Greg Theron. I'm a product manager at FeatureBase. Previously, I was a data engineer in the traditional BI space for a couple of years, and then the ML space for about 5 years or so, doing model implementation and data pipelines that feed models and that kind of work. But today, I'm going to talk about more of a analytics case with scale, maintaining up to the millisecond freshness across 20 billion devices. So it's one of the probably largest data sets and use cases I've worked with. But before I can get into that, I need to give a little bit of background on bitmaps. Probably something you've heard of, but don't know that much about. There will be a shameless plug for our company, FeatureBase, and our product and what we are. And then finally, I can jump into our use case with Tremor Video a little bit about more and talk about their massive scale and how I went solving about their problems from their original solution to the new solution. So let's jump into it. What are bitmaps? No, I'm not talking about bitmap images. I'm talking about these bitmaps. So bitmap is, lo and behold, a mapping from some entity down to bits, or said another way, a bitmap is a series of binary values that describe whether a relationship between two entities does or does not exist. So sort of have an example on the screen here, but you consider this kind of a transposed view of a table of customers and an indicator if they're premium or not. So up at the top, you have customers, and then you have a single bit set if that customer is premium, so they have a credit card and are paying. And that red highlighted piece is a bitmap, right? And it's easiest visualized by an array of bits, which is also why it's called a bit array sometimes. So why bitmaps? Well, essentially, they're just arrays of ones and zeros, which is machine code and can be read in by CPUs much more efficiently than other data types. And they offer a large reduction in disk and a bunch of other efficiencies that I'll go into in a second here. So I want to start with an example. So here we kind of have a traditional table, and we have a record for every single animal, and we're tracking their primary movement. So primary movement is the way in which they primarily move. And essentially in this traditional table, right, we have one record for an animal and one record for what their actual movement is. But we store the value of swimming for manatee, and we also store that value of swimming for seahorse. But I want to show you what that looks like with bitmaps. So here's that transposed view again. And this is what is really called a bitmap index. And you can kind of visualize this as a large matrix of ones and zeros. But essentially, each of these bitmaps is a pointer to a value in a column. So right, that first row is essentially an index to the value of flying itself. And what it really lets us do is instead of storing those values multiple times, so like storing flying multiple times and swimming, we only have to store those values once and then set single bits to indicate whether that relationship exists or not. So again, for something like swimming, we only set it once, and then we set a single bit for manatee, which swims, and seahorse, which swims. And to kind of take a step back on why this is really important in the database space is to go back and look at how analytics, what they had to deal with for like traditional row-oriented databases. So, we might have only had a column or two that we were interested in, but for row-oriented, we actually have to scan the entire table, right? It's a ton of that's a ton of IO to deal with. And then column-oriented databases came along and said, well, this is inefficient. What you should only do is pull the columns of interest to reduce that IO significantly. And that made life like a lot better. And bitmaps really offer a path to really go the next logical progression of that and let you index within the column itself. So if you look at that table on the right, you're essentially taking that state column that was scanned before, and now you're actually only scanning on the individual values of interest. So if I only am interested in Texas, right, I'm only scanning those records that have Texas as saved as a bitmap. And this is a massive reduction in scan and IO, and it's indexing at every single value, which is huge in terms of our ability to do analytics, especially at scale. So I talked a little bit of a basic example there, but this efficiency with bitmaps can be seen in a lot of different data types. Numeric, date time, with a strategy called BSI, which is bit slice indexing. I'm not going to go too far into that, but essentially, right, all these savings translate to disk savings that I've sort of showed an example, and that leads to a lot less scan for your databases. It also means a lot more of your data can be in memory, and which is great for compute. Bitmaps also are really great for logical operations, so ands, ors, nots, things like that, and aggregate operations like sums and counts and other things that we do for analytics a lot. Because at the end of the day, it's just a bunch of ones and zeros that those databases are computing on. So I guess why bitmaps now? Well, they're not really new. They've been around since the mid 1980s. In fact, you've probably heard of them before. They really were only introduced previously for low cardinality fields, to save on traditional space from like B trees and like RID, row identifier B trees. But there was complexity with them. Again, if it was high cardinality, you actually ended up having a lot more scan and IO costs than you did without bitmaps. And there's complexity when it comes to transformations and feature engineering on those. But you still find them actually, and you'll find bit slice indexes in a lot of feature bases, in a lot of databases today. So Postgres, DB2, Oracle, and us, FeatureBase. And despite the challenges, there have been a ton of advancements in the space. So more encoding techniques to allow for further compression on bitmaps. And even better, there's a lot of computation that actually happens on compressed bitmaps themselves. And big shout out to the Roaring Bitmap team for a lot of the work there in that space. And then just general technological advancements have happened that have taken a lot of the pains and challenges we've seen with bitmaps and greatly reduced them. So that does sort of lead me to my shameless plug of FeatureBase and what we are. So we are an ultra fast in-memory database specifically built for AI that provides continuous ingestion, updates, and real-time analytics on some of the most demanding workloads. And why this big lead up to us? Well, we are built entirely using bitmaps. So I don't want to do a bunch of marketing talk and whatnot. I just want to jump right into this use case. So Tremor Video is a client of ours. Tremor helps advertisers create dynamically personalized ad content in real time. They collect data from over 20 billion with a B devices. So that's TVs, phones, tablets, things of that nature, which touch over 40 million households and generate about 120 billion updates per day that they have to handle. And they need real-time data to create segments for really, highly targeted and personalized ads. Those segments have multiple devices, and the segment has a maximum of about 1 billion potential viewers on them. So we're talking like a really large segments and audiences here. And they offer solutions for both buyers and suppliers. So buyers on the purchasing of targeting information side and sellers to sell ad space. So they have a lot of data that they need to handle. And before FeatureBase, this is a rough look at their architecture. So all of their device information and segments came in on Kafka. That information was then loaded to 1,000 plus Hadoop cluster. Once it's there, they needed to perform like large aggregate queries and large group bys in order to evaluate segment performance and provide data that's needed for the transactions on their various platforms. So even once on disk, they had to use sampling techniques even to be able to batch and pre-ag this data so that it was available. And from the time they did this, it was anywhere from 24 to 72 hours until data was actually available for consumption. So that's a pretty long time. I have to say it's pretty common with my experience in this space. You generally find that at least a day behind due to batch loading, but even more commonly, in my opinion, about a week. So this isn't far from that. But let's talk about what ideal looks like, right? And what do they really want to get to? So they have to handle anywhere from about 500,000 to 1 million records per second. And that's not just inserts, right? It's inserts and updates. So new devices come in and existing ones need to be updated. They also want to have queries running on this data that are sub-second, and they want to have, at anywhere in any point in time, about 1,000 concurrent queries on that system. So that's really big. And I think we need to talk a little bit about the challenges we faced when taking this on. So the first is really the data model. And I'm going to start with how you might model this data traditionally. So you might do something where you have a UUID that represents, every sort of transaction or device segment pairing. And then you'd have a device ID that represents the device data is coming from, and segments, which represents information about that device. And the device and segment relationship is end-to-end, right? So one device can have any number of segments, and one segment can be on any number of devices. So, and to give an example of kind of what segment information is, things kind of advertisers might care about, right? So a couple on the screen is, a device might say, I've had 2 hours plus of on time today. It might indicate that this particular user is premium and is paying, or maybe it's got demographic like age bands of the actual users of the device. And thinking about this more in maybe a real-time context is information like, this device just turned on, or this device just watched show A, and stuff that really means a lot for the advertising parties. So again, we have 20 billion devices here, and thousands, if not more, segments. And if you do the math right there, that's trillions of records. And that's when you take that up over time, that's absolutely massive. And storing these segments over and over again, right? You can see where the space inefficiency really starts to add up. So this data model is probably not going to scale very well. And the question is, can we be more efficient here? Yes, but I need to introduce a couple of new concepts to you. So the first is a unique data type FeatureBase supports called sets. Sets are best visualized as arrays. So we support string sets, which are arrays of strings, and ID sets, which are arrays of positive integers. So I'm going to bring us back to that example of animals. And previously we looked at, what's your primary movement for that animal, but I think we all know animals can actually move around a couple different ways. So now we want to actually look at just the general types of movements of these animals. So a duck, for example, right? We know a duck can fly, walk, and swim. It's not just one of the three. But we don't want to store a record for each one of those, right? So we don't want to store duck 3 times, one for each movement type. And that's what sets really enables, right? We can have a single record and multiple values for that one record. I'm going to take us back to that transposed bitmap view of this information. And again, the big difference here is you can see that these animals now have multiple bits set for that same movement column. So it's really large space savings because we're not storing another record for each of those individual movement types. We're just setting one additional bit. Applying this to Tremor's use case. So now we don't need this UUID for every single transaction that comes in. We can actually use the device ID as the primary key of our table, essentially. And that's great because this caps our table. Now we stop at 20 billion records, and that only grows as more devices are introduced for Tremor. So that's great. That kind of stops this really scary growth of our table. And additionally, as more segments come in, they simply just get added to devices. That scaling just happens within that one column segments itself. Again, looking at that transposed view, you're going to have multiple devices that have multiple bits set. And anytime a new update for that device comes in, you're just going to set a single bit as opposed to writing a whole additional record. So problem solved, case closed. We're going to kick this off, and in 5 years' time, we're probably going to be good now, right? All right. No, probably not. Data is going to grow over time. We've all been there, done that. We're going to have to keep latency low. So we're going to have to address a couple of things in this data model. So how do we handle the growing pains here? I think the first is to look at sort of the traditional database view, and that devices most likely over time are going to be no longer valid. So maybe the device is just too old, maybe it stops sending information or breaks. For whatever reason, we know we're probably going to want some of these old devices cleared out. And this isn't anything new. You've probably seen this. So we're going to add an update time, right? And every time your device gets updated, we're going to update that time to whatever the current time is. And then we're going to pick some, time of some period of time where essentially we say, all right, this device is probably no longer working or being used, so we want to remove it. That example here, I'm showing it's 30 days. So let's say 30 days go by and you'll see those next top 2 records that haven't been updated are going to go ahead and be deleted. So nothing new here. That's a pretty traditional table and database workload, but it is important to keep up the maintenance of these. The real question is, what about this new growth? So we've kind of introduced something new with our data model in that we're adding these segments to each record, but over time, these are probably going to be less relevant to marketers. So this is like a little bit embarrassing, but I have a 10-year-old Roku at this point, and it kind of just, this use case made me think about it. Like if I'm getting personalized experiences based on things that I streamed 10 years ago, it's really not. My tastes have changed a lot, so it's really not going to be relevant anymore. So how do we address this problem? So again, I'm going to introduce something that you haven't heard before. It's called a time quantum, but what it essentially lets you do is associate a time with every single value that's in that set data type. So going back to our example in this table here, now when we take that device ID 1 and it tells us, hey, we've had 2 hours of on time today, we can actually associate a time of when that exact segment was added to the device. And the most logical time at this point, right, would just be that current time whenever it's shown. And this opens just a ton of opportunities for our queries now, because we can have generic queries that basically say, give me all the devices that had segments set between date 1 and date 2, or even more specific queries that say something like, give me all the devices that had 2 hours of on time between this date and that date. And that's really powerful, especially for marketers, because it gives that notion of recency and what's relevant to your advertisements more in their query's hands. So I think this is where thinking about a real-time use case really matters. So I was trying to think of one, and I'm assuming a lot of us out there watch Stranger Things in this latest season, and we got to episode 6 or whatever it was, and listened to Running Up That Hill. Well, if I'm Spotify, that's information I want to know right now, because I know you're going to want to listen to that song right after this episode, and I don't want it to be on Apple Music. I want it to be on Spotify. So it really matters, right? Like, this device just told you I watched that episode. It really matters that first couple hours or so, because I'm going to tune that, put it on, listen to it. But in the next couple weeks, months, probably not so much. And that's what time quantums allow, right? It allows you to basically control what's relevant in your data or not without losing any of the granularity. So I talked a lot about that from a data modeling perspective, but there are going to be challenges when you're looking at this type of scale outside of that. I've kind of highlighted 3 here, that there's no escaping bottlenecks from other systems. So accompanying software, hardware, and your operating system. And there are probably more, but these are the major 3 that we ran into during our time with this use case. So from a Kafka perspective, we actually had to set up a custom partitioning system where we had 64 partitions and consumers for each that would essentially write to specified partitions in FeatureBase. So really controlling that from the ingest perspective to speed things up. We also hit IO limits pretty fast at this, at a million records per second, you start really spamming your system. So we actually had to use binded SSDs with a RAID 0 system. And then from the operating system, we actually used Unix and we use mmap to bring files into memory. And it's just a limitation we hit. It's something we further want to optimize to get more speed out of the system. But to be honest, yeah, you're going to hit these. And the takeaway is don't be surprised to be in really low level problems when it comes to dealing with scale that is this massive. So recap, going back to Tremor, there's 1,000 plus servers or so, 72 hours max of processing time before people are actually able to consume the data. And ideally, we really want this to be a lot faster. So after applying just about everything I've covered thus far, what we ended up with was 11 nodes total. 2 are dedicated for ingest of updating and inserting records, and 9 were dedicated to querying in the consumption side. That led to a 92% reduction in memory and a 99% reduction in hardware, which is massive. And I think the biggest thing is, it took essentially days from them of sending this data in for ingest until they could actually query it and use it in their platforms and transactions. It took that from days all the way down to minutes. And to drill a little bit further into this, so we hit about a peak of 1 million records per second, and that's upsert transactions. So FeatureBase is naturally a upsert ingest behavior, meaning as soon as a record comes in, if it doesn't exist, we're going to insert it. If it does, we're going to update the particular attributes you send in, which in this case, right, would be those segments. And actually, a cool update we got this week. They came back to us and said we've been trying to fine tune more and scale up a little bit, and they hit a peak of about 6 million records per second, which honestly blows my mind. We need to dig a little bit further into what that is, but I thought it was a fun update to share. So it's pretty crazy when you think about this scale, but what it essentially means is we're running in memory just about 100% of the time, because every shard in FeatureBase is essentially being either written to or read from at all times. FeatureBase doesn't require you to run all in memory, but for low latency, right, that's essentially what you do want to do. Now, while this kind of ingest is occurring at 1 million records per second, we're still having our consumers and queries running on the system. So concurrent queries are happening, and it's no longer happening on the preag data, which is kind of the craziest thing here. There's no preag or batch processing. It's actually running directly on all 16 terabytes of their footprint. So 16 terabytes of data is being queried against, while 120 billion events are being handled per day. And I kind of just want to give a summary of everywhere we sort of trimmed down. So Bitmaps allowed us to reduce our disk usage a lot. They also have high compression and allow computation on those compressed bitmaps. This and the indexing it brings is a massive reduction in I/O for your database, and it's really performant when it comes to Boolean and aggregation operations. Sets let us make our data model much more efficient than it was before and allows us to scale much better over time. And time quantums let us filter those set values over time based on what's actually relevant to advertisers and their end users. We did have old-fashioned deletes, which is archiving the old records out because they're no longer necessary for this kind of real-time use case. And finally, there's fine-tuning in other areas. For us in particular, it was from the OS hardware and from Kafka. And that all led to these final results for this use case. So again, went from over 1,000 nodes to just 11 with FeatureBase, a 95% reduction in CPU, went from 120 terabytes of RAM just down to 11. Data freshness, which is essentially how fast it is from the time you go to ingest data to when it's accessible to query, went from about more than 24 hours down to minutes. And data latency, which is the latency that your queries actually return, went from anywhere greater than 12 hours down to less than a minute. What's not here and is great for Tremor is that they're saving about $5 million per year in terms of hardware costs. But the most important thing is that this is a like true competitive advantage for them, because no other competitors are able to give this information at sub-second results on such large data, and that's a huge impact for advertisers and what they can do to personalize their ads and experience for users. So that's about it from me. I really hope you take away how cool bitmaps are and consider bitmaps in their future and learning more about them. If you didn't believe in this presentation, I can totally understand, but I'm happy to say we are open sourced as of late last year. So you can feel free to go to GitHub at FeatureBase DB and download us and put us to the test. Finally, this was really an analytics use case looking at scale, but we're really excited for more ML workloads. If you think about our data as a binary array, it's really a logical pairing with linear algebra and the math behind many modeling techniques. So I'd love to see you come to the community, toss out your ideas, prototypes. We're at FeatureBase DB in Discord, and I'd love to toss those ideas around with you. You can reach out to me there. I also have my email on this presentation. So either way, love to hear from you. Otherwise, thanks for taking the time, and have a good rest of the conference.